All right, ladies and gentlemen, we are going to be talking about the couple different types of right hand rules today. Yesterday, we discussed one type of right hand rule that we used, where we said our thumb, if you basically make an L with your index finger and your middle finger, and then point your thumb upwards. Um, we use those three fingers where your middle finger is a magnetic force, your index finger is a magnetic field, and your thumb was a particle's velocity moving through that magnetic field. That rule that we used yesterday was actually the third right hand rule. And today we're going to explore a couple others. We're going to talk about a couple others. So make sure you finish do your exit ticket for the day. And then the assignment that we had yesterday, it was called day 9 and 10 assignment. Make sure that you finish that up today. The only questions left on there should be numbers 2 and 4. So pretty easy assignment for you today. All right. So we're also going to be determining the direction and magnitude of magnetic force, except we're going to be determining it in a little bit different fashion here than we did yesterday. So I encourage you to go through and watch this video here. This guy talks about three different right hand rules, and I think he just does a really good job of describing them. And he's got great pictures on his board. So please go watch that before you actually watch this video, or before you finish this video. So if you want to pause this video and then go watch that video, do that now. But yesterday we used the third right hand rule where we were talking about a particle moving through a magnetic field. Today we'll use the second right hand rule, and I'll briefly talk about the first right hand rule. We may or may not get to using it, but I'll talk about it anyway. So this would be our first right hand rule. Okay, so this is first right hand rule. Okay, and this is just talking about the magnetic field that is created around a wire when you have current running through it. When you send current through a wire, you are creating a magnetic field around it. You're essentially making what is called an electromagnet. We can use electricity to create a magnet. A common lab that I like to do if we were in class is if you take current and you if you take current and run it through a wire, and then take that wire and wrap it around a iron coil or a nail a bunch of times, you can actually get the electrons within the nail to get spinning in the same direction. You create a giant electromagnet, and you can take that nail and you can actually pick up small things like paper clips. But what we're doing here is we're causing a movement of charges, and that's going to create that magnetic field around that wire. So hopefully you watched that video that the guy explained the three different right hand rules. But the first right hand rule is basically just taking your four fingers and they curl in a direction. Your thumb is the current, and whichever way your thumb is pointing, this is where the current is going. And then your magnetic field curls in the direction that your four fingers are pointing. So that is our first right hand rule. I'm not sure how much we're going to get to that one, but just in case we do, it is there for you to use. For a force on a wire in a magnetic field, this one we're going to be using. This is our second right hand rule. This one we'll be using a lot more. Luckily, this one is essentially the exact same as our as our third right hand rule. So remember yesterday when we talked about third right hand rule, okay, that was dealing with velocity, with a velocity of a particle moving through a field. The second right hand rule, you still have the exact same two vectors on your fingers. For your middle finger is still force, your pointer finger is still going to be your magnetic field, and then your thumb is actually going to be current. It's the only difference. So now we're talking about having a wire running through a magnetic field. and what force is going to be put upon that wire within that magnetic field. And in a little bit here, I got a video that shows a really good demonstration of that. All right, but for this equation, similar to yesterday's equation, instead of using charge of a particle and velocity of a particle, now we're going to be taking current running through a wire and length of the wire in order to solve for the force. So we're still using B, which remember from yesterday, B was equal to my magnetic field, and that is measured in Teslas. And then we also have I, which we know is current, and that is measured in amps. And then finally we have L, which is, oh, that's supposed to be an L, which is length of your wire. Length of your wire that is parallel to or within the magnetic field. So we are actually going to just be measuring that in meters. So make sure if you're ever given a wire in centimeters or something like that, you actually convert it into meters. There is supposed to be sine theta in this equation, just so you know. Just like yesterday's equation, I just ended up taking it out simply because we're always going to use it as B and or the field and the current perpendicular to each other. We're not going to make this super complicated. So essentially that sine of theta will always be 90, so it's just going to end up being 1. Okay, so let's go ahead and put this to some use. I think actually I have this video first before you move on to the problem. I encourage you to watch this video. This video does a great job. He does a great job of showing what exactly it's going to look like as a demonstration. So he's got this magnet here. This is a giant magnet, and I can't remember which one's north and which one's south, which way the field is running. But the field is either going to be running up or down, and then he's going to have in here current running through the wire, either to the left or to the right here. And then you're going to see that the force on the wire, you're going to see the force either go in towards the magnet or away from the magnet. All right, so it's just a really good video, so I'd really encourage you to watch that. All right, so actually putting this into an example, we have a wire 36 meters long, carries a current of 22 amps east to west. The max magnetic force on the wire at this point is downward towards Earth and has a magnitude of 4.0 times 10 to the negative second newtons. We need to find the magnitude and direction of the magnetic field. Okay, so I'm just going to start writing down a few things of what I have. So I have a wire 36 meters long. So that's going to be my L, 36 meters. And then I'm going to have current, 22 amps. So I have current, which is I, 22 amps. And then I have a magnitude of, now this is the magnetic force. So I'm actually given force in this problem. 4.0 times 10 to the negative 2 newtons. Now we need to find B. All right, that's the whole goal here. We need to figure out what is B. Well, going back to our equation of F equals B I L. You can just go ahead and plug everything in here. So I'm going to end up with 4.0 times 10 to the negative second is equal to B, which I don't know, times 22 times 36. Take a second to pause the video if you want to solve for that. B should end up being, I lost my answer. should end up being 5.1 times 10 to the negative fifth. And that is measured in Teslas. All right, now the last thing we need to do is that's the magnitude. We need to figure out the direction. So this is where your second right-hand rule comes into play. So just like yesterday, take your index and your middle finger, make an L, and then point that thumb up. And you are going to use, we will say that the current is going from east to west. So let me just kind of color coordinate here. Current is going from east to west. So we'll just call that this direction. So that's my current. And then I have my force. I'm trying to match colors here. My force is pointing downward. So we'll point this downward. That is my force. So now I want to I'm going to point my thumb to the right, and I'm going to point my middle finger down. And then what you should have is you should end up having your pointer finger pointing right at you, and that's going to be the magnetic field. So if I were to actually draw this as, I'll make this green. If I were to actually draw this, I know we're dealing with, I wanted green there. If I were to actually draw this on paper, if it's coming at me, I would just do that dot like it's coming out of the page. So in this case, if you wanted to say out of page, you could do that. Otherwise, if you would rather, since we were technically using the terminology up here, east to west, and we're deeming basically right as, oh, I did that wrong. Let me go ahead and fix that. East to west. That is why I messed that up. We're going to restart that, ladies and gentlemen. Sorry about that. Let's try that again. East to west is actually going to be this way. Look at me not being able to get my compass rose down. Okay, and now let's try that again. Okay, so now we're going to have our force downward. So now we redo this, and we'll have our current actually pointing to the left. Force is pointing down, and now we're actually going to be going into the page. My apologies. Into page. Okay, so this would actually end up being an X going into the page for my magnetic field. So you can either say into the page, kind of back to where I was headed with this, you can either say into the page, or since we're deeming this direction of the current as west, just like a compass, and this force is downwards towards Earth, if you wanted to, you could say the B field is going north. So I'll just put or north, because if we're on a 2D surface, so technically that would be to the north. Okay, my apologies about the mess up there. It just seemed I didn't want to make a whole new video. So if you have any questions, please make sure you let me know, email or in a comment on Google Classroom. Have a great day.